based on a joint work with Peter Kukoschka from Colorado State University, his PhD student Sunmin Lee, and my colleague Tim Kutafo. And so the type of matrices that we want to monitor are Wigner matrices, but really, so maybe first things first. So why are we interested in Wigner matrices? So the reason is that they can serve as idealized models for network. On the other hand, we know that they share some important property, other type of network data that we might be even more interested. So while the talk that I will today is kind of tailored to Wigner matrices in our paper, revised version of the paper, which is available soon, we also show that this exact test statistic that I'm going to show you also applies to a much larger class of data, so that you should not only think about the Wigner. But I think it's a very good point to start with. Okay, so for this talk, I will first talk a little bit about Wigner matrices, what they are and what kind of properties they have that are interesting in relation to the topic of my research. And then there in the second part of this talk, where I will introduce some monitoring procedures, so what kind of point setup we are interested in, and then we will kind of combine the things with Wigner matrices. Okay, so let's get into Wigner matrices. They are really the most standard matrix ensemble in random matrix theory, so you may or may not have heard about them. We will consider a Wigner matrix of dimension n, and this means that this is n times n matrix. It is symmetric, and up to this symmetry constraint, all the entries should be independent. And then we have a certain class of moment conditions. So we want the entries to be centered. We want, the second moment to be of a specific form, namely that it has a fixed variance along the diagonal entries. So sigma squared plus c is the variance on the diagonal, and then for the off diagonal. And then for convenience, we also need some higher order moment, so here in the order. Okay, this is the Wigner matrix, and something that you can always think about is the Gaussian case, so the so-called Gaussian orthogonal ensemble, or GOE. And this basically consists of a symmetrized version of matrix with IID entries. So I take the relation post, and then if I do normalization, easy to see that this is indeed Wigner matrix, and normalization will cause the sigma squared and c both. Okay, so this is the Wigner matrix, and in the data that we observe, think about the Wigner matrix being our noise. And so we will consider the so-called formed Wigner matrix. So we add a rank 1 signal to this Wigner matrix, and the question is, when can we detect this signal? So how large does this S need to be in order that it's louder than the noise? So S here, for a second, I'm going to assume that it's a fixed deterministic number, but later on it can also be. Then the X is a unit vector. For a moment, I will also assume. Okay, and if you think about a setup where n, so the dimension of the Wigner matrix, gets large, then when the matrix theory actually answers this type of question based on spectrum, so based on eigenvalues and eigenvectors. So it says that there is a critical threshold, which in this model of this rank 1 deformed Wigner matrix is a sigma. So sigma was here this term in the variance of the Wigner matrix. So sigma will be this critical threshold, and if the signal strength is below this critical threshold, then essentially you cannot detect the S by looking at the spectrum, because the largest eigenvalue of this deformed Wigner matrix will converge to something that is independent of S. And also, if you consider the eigenvectors, so U1, an eigenvector corresponding to this largest eigenvalue here, and you consider the x, so the signal, then asymptotic will be these two things will be orthogonal to each other. So no information about the x and no information about the s. On the other hand, if s exceeds this critical threshold, then the largest eigenvalue will converge to some function of s and signal. So this time you can learn something about the s, and also the angle between these two, so it converges non-trivial. So the formulas itself are not too important for our talk. So what I just want to summarize here is that in the subcritical case, actually, we have no information about the signals, so no information about s and x, whereas in the supercritical case, both the largest eigenvalue and the corresponding eigenvector gain meaningful information. So all these type of things are very well understood in this random matrix framework, where you have just one matrix. So you have a Wigner matrix, and you ask this type of question. But actually, if you think back to the beginning of the talk, I told you that we want to consider a time series of Wigner. So later on, we will have a stream of data, and each data point will be deformed. So just to give you, okay, so before we turn to the monitoring of the Wigner matrices, I want to introduce a kind of change point model that we're in our general idea. We want to consider the sequential change point detection problem, and I will explain it here by considering the example of monitoring for a change in the mean. For this part of this talk, 5 minutes, they will not be about Wigner matrices at all. You can just think really about real value data, and you want to monitor for a change. And then our setup is like this. So we assume that there's a training sample. The size of the training sample will always be n, and within this training sample, there's no change. So here the data has a constant. Then at each time point in the monitoring period, there arrives one new data point. And then we would like to decide whether there was a change point based on the training sample and the additional data that we observed in the monitor. So at each time point k in the monitoring period, we take all the data that we collected up to this point to decide whether there is a change in the mean or not. So the null hypothesis is constant here under the alternative hypothesis that it's constant up time n plus k star. And then it jumps to a different. I think it's probably easiest to explain this type of paradigm by using illustration. So this is a simulated time series. And here at time 400, we implemented a change in the mean. Here is a change. And then we can start and maybe we say that, okay, this first 100 data points, they will serve as our training period. And then get one data point added. So for example, if we are in time 1 in the monitoring period, we have 100 data points from the training sample and one additional data point. And then we do our procedure to decide whether there was a change or not. If we believe there was no change, which we hopefully will at this point, then we would continue monitoring and we get more and more data. So here at this green dashed line, we are at time 200 in the monitoring period, so we get 200 data points here. And then again, ask our detector, is there a change or not? And if not, we will continue. And then at some point, we will cross this change point. Of course, in reality, we don't know that there is a change point. But for the simulated example, at some point, we will cross it. For example, here at time 350 in the monitoring period, we would maybe come to the conclusion that there was a change in our time series, and at this point we will stop the monitoring. So the idea is we will monitor as long as we don't do the change, and then we will stop. Then probably you want to do something about it. For example, if you do wildfire detection, one of the examples in our data set, then you would do some action if you detect the wildfire. Okay, so that's the idea of sequential monitoring. And now I would like to name our Wigner. So this is how our data at each point t will look like. So it will be the matrices n from before. So this rank 1 deformed Wigner matrices. But yeah, at each time t, we get a new Wigner STs here, which are the signals, the X, which are these units. And then we want to monitor for the following probability of the ST. So we want to see whether this S is distributed according to a probability measure P1 or P2. So I should explain what these two guys are. So P1 actually refers to the regime where the spectrally there's no information about the signal. So we're in the supercritical case. And this will also be the initial state. So this will be the state for the training. And then P2 corresponds to the supercritical case where we learn some. Okay. And then, as I said, for the training sample, we will assume that we are in the first case, so all the signals will be distributed according to P1, which means that in the training period, spectrally, we cannot detect a signal in our deformed Wigner. Then we start monitoring. So at each, we get one matrix, and we want to use all the data that we have, so, data from the training sample and all K matrix from the monitoring period to decide whether the ST is still according to the distributed according to this probability level P1, or if there is a change in the distribution, a change towards the supercritical. Okay. So how much time do you have left? I'm not sure when we started.
Roughly 3:15, I think. So
okay. So,
yeah, we have some time.
Wonderful. So I can use this time to explain you how we approach this problem. And if I tell you how we approach it, maybe we should first agree on some criteria that we want our test to fulfill. So we want to develop a test for this problem here. So for detecting a supercritical signal in a weakly time series of high-dimensional matrices, which are Wigner matrices. And here is the kind of setup that we think about. So M was the training sample size, should be in a polynomial relationship to the N, where N was the dimension of the Wigner matrix. And under the null hypothesis sequence of triangular arrays, so the Wigner matrix, the axis, and the signal strengths, they should be strictly stationary under the null hypothesis. And well, under the alternative, there will only be. And in terms of time dependency, we think here about the findings. And then we have two goals for our methodology. So first of all, under the null hypothesis, we want to be able to approximate a nominal level alpha. So approximation here means with respect to this asymptotic regime, so M and R in a polynomial relationship, and we want power consistent under the alternative. I think this is something that we can all agree about. So let's think a little bit about the statistic that we want to use. And this is inspired by some kind of result in random matrix theory that again will only hold for one matrix at a time. If you fix the T, then consider the largest eigenvalue. So the lambda t is here the largest eigenvalue of an MT. And if you scale and relocate this eigenvalue the right way, then this will give you some kind of nice limiting distribution here. TV, which stands for Tracy-Willem distribution. Don't worry if you're not familiar with the Tracy-Willem distribution. Too important how it looks like from statistical purpose. You only need to know that it's pivotal, so it will not depend on any unknown part. So this is the case if you're in the subgroup. However, under the in the supercritical case, this thing here will explode because this n to the 2/3 is not the right scaling in the supercritical. So I think this is a really nice starting point for a test statistic because you have something that where you can compute the quantiles under the null hypothesis, and that will explode under the alternative. So one idea, use this result across all the different T's, would be to consider a very well-known statistic, namely the QSIM statistic of these eigenvalue functions. And we see that if we consider this type of QSUM here, what is really nice is that the sigma, which is unknown to us, so the variance of Wigner matrix, it will cancel out. So in the end, we even have something that, so I think this is a very natural idea for a test statistic. At least it was the first idea that we came up with. So the question is, can we use this statistic for testing what we're interested in? And well, I think there are two main problems here. So the first problem will be that while if I consider every single n to the 2/3 number t, it will have some nice limiting distribution that does not depend on any unknown parameter. But of course, if I kind of sum over the t, if I hope that there's a nice limiting distribution, then this limiting distribution will somehow depend time dependency of this time series here, which is of course unknown to us. So I think this is a problem. And another thing is a theoretical problem. Maybe kind of what I suggested here is that if we use this test statistic, then hopefully it will behave like this. So I can just substitute these kind of limits that we know from ornament. However, I've already warned you a little bit about it, so this is not possible because these type of results only hold for one matrix that gets a large dimension. So for n fixed and n gets large, but we don't have these results like uniformly over k and also in the limit with n. In fact, it's not even known whether the moments this year will converge to the moments of the traceability. So it's really not clear if we can hope for something like this. Yeah, I don't believe it's this. So this is not exactly what we can use, but fortunately, there is one tool in the literature that will solve both our problems at once, and this is the idea of self-normalization. So the idea is that we will construct a normalizer Vn, and this normalizer cancels out long variance so that it makes our limiting this asymptotic load. And it will also help us to get rid of this type of problem here, this more theoretical. Get both, we get two for one. Yeah. And what I just want to emphasize here is that self-normalization is really not the same as the estimation of the long run. So in self-normalization, we would divide by this normalizer Vn, but this normalizer itself has a non-degenerate limiting distance that is constructed in such a way that it's proportional to the long run. But it's random itself, so it is not an estimator for the long. It will just have the effect that it cancels. So this is the normalizer that we come up with, and so the exact form is not too important. So this n to the 2/3 is kind of motivated concentration results from random matrix theory, and this 1 over m to the 3 divided by 2 comes from the typical order of this type of QSUM statistics. But what is important to note here is that it draws only on the training samples, so only on the time period where we know that there is no. Okay, and then our final task statistic will consist of this gamma tilde that I motivated before, where we have this QSUM type eigenvalue statistic, and then equipped this denominator em asymptotic. Okay, and then this is the type of result that we can expect here. So I'm not going to talk about it in very much detail. So there are some technical assumptions that we're going to have, but some of them I presented them to. For instance, we have the phi mixing time series. Then under the null hypothesis, we can get this type of approximation. B here is a standard Brownian motion. So this is a type of standard limit here in the numerator that you may expect if you are familiar with QSUM statistics. And then here, this arises from the self-normalization. So this sum that we have here, it will converge to some integral where where here again we have, okay, so this is a type of result that we're able to prove under the null hypothesis. And then, of course, you can construct a level alpha test from this. So at each time point k in the monitoring period, we would then inject null hypothesis if our detector gamma, so two parts, if this is large, so if it exceeds 1 minus alpha point, is limiting. So and let me say that can simulate quantile. And then, of course, you get the following results. So under the null hypothesis, this will give you the desired level alpha control asymptotically in M and N. So in our paper, we model N as a function of M. So this is the reason why you only have this in N here, and control the supremum over your detectors under the null hypothesis. And we are also able to prove some power consistency result if the change is not too late. So if the change is in polynomial relationship to the training sample. So okay, so let me conclude this talk. So as I already said at the beginning, what you should really take away from this talk is that this type of phase transition detection is possible for a broad class of high-dimensional random matrices. So for today, I showed you how to do it for Wigner matrices, but from random matrix theory, we know that there are a lot of matrix models who spectrally behave similar, or at least not too different from a Wigner matrix. And to this class of matrices, the procedure is also applicable. And the cool thing here, I think, about our work is that we use this type of self-normalized detector, which is based on the extremal eigenvalues. And for the methodology, it's very nice because you don't need any tuning parameters. And also it kind of facilitates the theoretical. And I explained to you that it's not really possible to use much results from random matrix theory because they just hold for an individual matrix. But what this self-normalization will do is that it kind of enables us to do Gaussian approximations for these eigenvalues. And this is something that we could not do without them. And so the theory that we use in our paper is based on some concentration results from random matrix theory, and then we combine it with Gaussian. There are also nice application, real data examples in our paper that I did not have the chance to talk about today. I already mentioned this data example where we do wildfire monitoring, and we see that our procedure will detect the wildfire shortly after it was there. So I think that's very desirable. And we also have another data example on the social interaction between them. Okay, that's it for today. Find more details in our preprint, but I'm also happy to take them. Thank you very much.